Hello everyone, welcome to the control system. This is part 5 of lecture 5, block diagram. And in this section, you are going to learn block diagram reductions. Okay? And as you know that the block diagram representation of the system involves summing point of functional blocks and so on. And those functional blocks are interconnected. In many cases, the connection are complicated, so such complex diagram must be reduced to its simplest, right? The simplest form. Okay, so there are some certain rules that we need to apply to reduce the block diagram. For example, the first case is a combination of the block in cascade. For example, you have two blocks like this, and if you want to combine these two blocks, it's simple. Just multiply this G1 and G2 together. You can see it is shown in this figure. Okay. Mm, so so if they are connected like this, very simple, but it is important to note that the loading and interactions between the connected components or system may occur. So if the loading does occurs, we must account for this change into the transfer function and use the corrected transfer function, okay, in the subsequent calculations. So we need to add it into the block. And the second one is moving a summing point behind a block. For example, you have the diagram shown like this, and you want to move this summing point into this part. So in that case, you need to add this g right here too, because the math have to be consistent. Okay, in this case, x1 plus x2 times g will be equal to x3. And if we want to move like this, we need to add g here, so that x3 will have to be the same. All right. Another one is moving a pickup point ahead of a block. This point. That can also be called branching. Okay. If you want to move this to this direction, so in this case, you need to add this block. Okay? Because why? x2 is equal to g times x1. So this is x2, this is x2. So x2 here, g times x1, x2 here equal g here times x1 as well. Next is moving a pickoff point behind the block. So if you want to move this to this part, so in this case you need to add 1 over g here, okay, because this x1 have to be the same to this one. So this one times this one have to be 1. Okay. So next is moving a summing point ahead of the blocks. Okay, so for example, you have the diagram like this, and it can be transformed to this one. Okay, so there's only a little change, but x3 have to be the same. Very simple. And next one is eliminating a feedback loop. So this you have already studied in the previous part of these lectures, and you derive the equation to get the feedback loop already. So the first one that you need to check is this one, cascade. Very simple one. Okay? And then you can check all of this rule if you want to do the simplification. So next, to draw a block diagram for a system, we need to first write the equations that describe the dynamic behavior of each component You can obtain this using, for example, Newton's second law, uh, the most popular one, or Lagrangian. Okay, so this is physics and math. You have to combine it, and then take the Laplace transform for this equation of these equations, and assume zero initial conditions. Okay, so only two steps: get the mass, and then do the in time domain, and then do the Laplace transform. So you need to transform from time domain to S domain. So it is important to note that the block can be connected in theory only if the block of one block is not affected by the next following block. Okay, let's move to the example. Okay, so in this case, we'll consider RLC circuit. Okay, let's recap a little bit before we proceed further. So the resistor, for example, the voltage across the resistor is just I times R. Okay, and if you wanna write in terms of S, okay, in Laplace domain, so Vs equal Ris. So this R is constant. So you take Laplace both sides. But we're gonna use a lot of Laplace transform, and if you don't remember, you should go back to lecture 2. So we use a lot of Laplace transform. This is for resistor. And next one is for inductor. Okay, inductor, the voltage across inductor is just L times di dt, and the in terms of Laplace transform, you can in terms of S, you can write like this and assume initial conditions. And inductor is just I, so this is the current in the inductor is just C dV dt. Okay, and then you can do the Laplace transform, get this one. If you want to obtain V or Vs, so Vs equal Is over Cs. Okay. All right, so let's consider a theory of RLC circuit as shown in this figure. You are familiar with all of this already because we study modeling electrical system in the lecture 4, I guess. So this is an input voltage, and this is the voltage in the inductor, and the current flow in these directions. Okay, we have the resistor, we have the inductor, and the capacitor. And then if you do Laplace transform, you will obtain this one. All right. So it just, yeah, you can use this expression. Oh, this is Is. Okay, this is Is. Okay, and from the circuit, we can obtain Is. So Is equal voltage Vis minus V0s, and over this R plus SL. Okay, so the voltage across this. And then the voltage in the inductor here, V0s, equal 1 over SCIS. And then you can write a block diagram, okay, using these two equations. Okay, for example, this is a summing point, and we have Vi here, Vis. This is plus, this is minus. So you can see Vis minus V0s here equal to what? Equal to nani? Oh, sorry, I talk in Japanese. So 1 over S times Is. This block. Okay. And you can also write a relationship between Is and V0s. And finally, the relationship between VIS and V0S can be obtained from the previous equations.